Hello and welcome back to the shortest lecture, but the coolest and the most powerful lecture of Calculus 2. Calculus with power series. Last lecture, I mentioned the integral of sine x cubed dx. And we calculated that. Let me steal it from the previous so I don't have to do it again. It's right here. We calculated this to be the power series. So copy. And then go back here. We're going to paste. Say there. So approximately equals to the integral of this dx, and then we labeled that as a joke. So we went from a problem that we can't do into a joke, right? Now, in between, we had to know power series. To find power series, you have to know the derivatives if you don't know the power series, and right? So there is a lot of that. So integration and differentiation for anything now would be step 1, turn it into polynomial. Step 2, just, differentiate or integrate. And the lesson is over, right? You have the example already. There are a few subtleties that we have to take care of. Here is a very important thing that you have to be very careful about. Remember that the power series are very, very, very sensitive on where you compute them. So when you have the integral, that integral is going to have some limits. So if you have the integral of, let's say, e to the x squared, there's another one that you can't compute without x in the front or some other witchcraft. So you are looking at this thing, and let's say that they are interested in the integral like 5 to 7. Can you just go and say, okay, expansion for e to the x is 1 plus x squared over 2 plus... No, because this thing here, let me just do that. This thing here is centered at 0. Now look at your interval. Where do you have to center it? At 6. Okay? Need to center my power series at 6, because that's going to be midway between 5 and 7. So now I'm going to have my power series for E 0 to infinity of x minus 6 to the n divided by n factorial. If you memorized that e to the x centered at 0 is summation x to the n divided by n factorial, then if you need to center it at some other value, it's just x minus that number. Now that goes for every single one. If you memorize sine and cosine and hyperbolic sine and ln of 1 plus x and all of these other ones, if you memorize them for whatever reason because you love it, the matter of shifting is just put x minus whatever value you need to center it at. So now I have that my e to the x centered at 6 is going to be 1 plus x minus 6 plus x minus 6 squared over 2. And let's do one more term, x minus 6 cubed over 6. Oh, this is approximation because I chopped it off. Now, people don't care about your x. They want x squared. So each one of these x's needs to become x squared. And now e to the x squared becomes 1 plus x minus 6 squared plus x minus 6 to the 4th over 2 plus x minus 6 to the 2 times 3 is 6 over 6. Work out these polynomials, and all of a sudden you can integrate, and you integrate 5 to 7. So now it's integral 5 to 7 of this stuff, dx equals joke, because it becomes a polynomial of the 6th degree, right, when you FOIL. Now, obviously, foiling over here is going to be annoying, and it's going to take a long time, but guys, compare the problem that you can't do at all to a little bit annoyance to multiply and FOIL some polynomials to actually be able to do this. So that's a huge gain, actually. Going from something that cannot be done into something that you actually get to do. So you have to be careful with the limits of integration, and you have to make sure that you are centering your Taylor polynomial either in the middle of the interval, or if the values are close by. Maybe you are calculating integral from 1 to 1.2. It's okay to center it at 1. You can center it also at 1.1, but that's just going to be a lot more annoyance. Because from 1 to 1.2 on the interval, that's not going to be that much issues with that many issues with the Taylor polynomial. Now 5 to 7 is a big problem if you center it at 5 and then there is 7 2 units away. So center it at 6 to minimize the amount of error. The last thing that I want to show is another one of those things that you never asked why, you accepted it. Now you did see a proof. If you sat in my Calc 1, you definitely saw the proof. What's the derivative of sine? Cosine, huh? Why? Then you have to go and you break your back through that procedure with the limit, and then those sum formulas, and those two limits that you had to memorize. I can pretty much bet money that no one knows that proof right now in the class, because it's just way too many little things to memorize and remember. How about we ask our friend Taylor what's the derivative of sine x? Because what Taylor polynomial are going to do is they're going to replace sine x with x minus x cubed over 6 plus x to the 5 over 120 minus x to the 7 over whatever the hell 7 factorial is, plus dot dot dot. And we are differentiating a polynomial. Derivative of x is 1 minus derivative of x cubed is 3x squared divided by 6. We have to cancel that. Plus 5x to the 4 divided by 120, have to cancel. Plus 7x to the 6 divided by 7 factorial. Oh, that's a minus there, sorry, minus. And then plus dot 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 going on forever. So now when we cancel here, we get 1 minus x squared over 2 plus x to the 4 over 24 minus x to the 6 over 6 factorial, because 7 factorial is, right, 7 factorial is 7 times 6 factorial, and then 7 and 7 canceled, right, because there was a 7 on top, and you just have a 6 factorial on the bottom. Plus dot dot, what do we know when all of the powers are even? And we have alternation minus plus minus plus minus plus. Yeah, it's a cosine x. Cool, huh? Now you take the derivative of the cosine x, and you are going to get minus sine x. Derivative of 1 is 0. derivative of x squared is 2x, and then 2 and 2 cancel, you just get x there, right? But it's a minus x. And that's a plus x right there. So all of these signs are going to be opposite. And you get the negative sign. It all has to click like that, like a puzzle. So derivatives, and now you see that the derivative of sine is cosine. So next time when someone pulls it off, this is a good conversation starter. Let's say Thanksgiving dinner, you go out, right? You can start right there. By the way, did you know? That's a good way to begin. Or, let me show you a cool thing, because you had the napkin ready and the pen, and you just crank this. You're guaranteed to play video games forever in peace. See you Monday.